Now let's talk about the production side of this economy. The production side of this economy is going to have two levels. First, we will have the final goods level. The final goods will be assembled from a bunch of intermediates. We're going to label them J, and J is going to be drawn from the 0, 1 continuum. Suppose that final output is Y sub t. This is going to equal an aggregate of the intermediates. So it's going to be the integral across all the intermediates. Now let Y dated t of J be the use of each intermediate, and we're going to make this a constant elasticity of substitution aggregate. So this is going to be raised to the power of epsilon minus 1 over epsilon. Then this whole thing will be to the power that is the inverse of the first exponent. And you can verify easily that this means that this is homogeneous of degree 1. It is assumed that epsilon is greater than 1. Epsilon is the elasticity of substitution between these different intermediates, and this implies that they are substitutes. Now suppose the final good sells for price P sub t, which is competitive. Each intermediate has price P sub t of J, and we will discuss later how those prices are set. That's going to be the whole deal with Calvo pricing. So the final goods producer maximizes. Well, they're trying to maximize their output times its price, this is revenue, minus their costs. And their costs, of course, whatever they have to pay for each of the intermediates. We can replace output with this expression, and so what the firm is doing is maximizing this with respect to each and every yj. Let's take the first order condition of this with respect to any particular yj. Each yj is inside this whole expression, so the first thing we need to do is derive this expression. That means that this exponent comes out, and we need to subtract it by 1. Next, we need to figure out how this expression depends on each yj. Well, it depends on it like this, and so we need to derive this independently. So we will get that we have to multiply everything by the exponent and also subtract 1 from the exponent. Now, if we derive this with respect to any particular yj, all we end up with is the price. And of course, in the optimum, all this has to equal 0. There are many obvious simplifications here. If a minus b equals 0, we can just say that a equals b. This clearly equals 1. We can simplify these powers by just observing that x over x equals 1, alternatively epsilon over epsilon equals 1. Since we have common denominators, we can combine these terms, and that means that we end up with this. We can play the same game here. This 1 can be expressed as epsilon minus 1 over epsilon minus 1, and combining all these terms, we end up with this. Next step, let's divide both sides by pt. Great. And let's raise everything to the power of minus e. Why do we want to do that? Well, let's do it. And sorry, by e I meant epsilon. What's going to happen here? Well, this stays as it is. Notice that we multiply these powers, and so this becomes 1. This becomes minus epsilon. And furthermore, notice that this whole thing is just output, except that it's got a minus sign here on its exponent. So this is just y to the minus 1. So finally, when all is told, we just have that the demand for any particular intermediate is based on aggregate demand and some function of the relative price of that intermediate. Now, before moving on, we are in a good situation to derive how the aggregate price index depends on the individual price indices. So, notice the following. Since we have constant returns to scale, that means that total production equals total spending on inputs. Total production is PT YT in nominal terms, and total costs are this. And all of this, because there are zero profits, equals 0. Therefore, we have that these two things have to be equal. Now, using this expression, we can substitute for the demand for individual goods and get this expression. We can separate this power over the two arguments here. And then take this out of the integral. There are several things we can do now. We can divide both sides by yt. And we can also combine this with this to end up with this simplification. Notice that PT doesn't depend on J, so we can multiply both sides by PT to the minus epsilon. We end up with this. This simplifies to the following. And so we end up with the following expression for the aggregate price index. This is something that's going to be useful later on. Now let's look at the intermediate producers. And this is where Calvo pricing is going to come up. Now let's ignore capital because we want to focus on the whole pricing issue and not worry about any extraneous complications. So each intermediate producer faces the following production function. Yt of j is going to be their output, and there's going to be a productivity term, which again we've looked at before and is common across all firms, and you have to choose their labor input. There is a common wage W sub t, which is competitive, so that describes their cost structure. What about their pricing? Their pricing has a particular structure, which is called specifically, there is a pricing contract. And this pricing contract has the following requirements. First, given the price, firms must satisfy demand, regardless of whether or not they make positive profits. Second, the price is the same as last period's price with probability phi, and with probability 1 minus phi, the firm can choose what it views as the optimal price, given that it will have to then agree to the same kind of contract. With probability 1 minus phi, the firm will choose a new price, given that it will be subject to the same kind of contract. In other words, the firm chooses a price, it commits to meet demand at that price for the duration of the contract, and the contract ends with probability phi each period. Now, a firm that is stuck with a price of P sub t of j earns nominal profits of, well, they sell P of j times y of j minus the nominal wage times whatever their labor input is. But we are interested in real profits. So real profits will be the same thing deflated by the price index. And we're going to give this a name. We're going to call it pi of j. Now, let's define the following variable. We're going to call it MC, which stands for marginal cost of t, equals 1 over A, which is the inverse of how many units of goods you can get from a unit of labor, times the cost of labor in real terms. Of course, this is equal to the real wage divided by its marginal output. Then we can redefine profits in terms of this MC variable. And you can see that since n is y over a, we can simplify this as simply this times the real marginal cost term. Now, here we only have one input, so if there were multiple inputs, such as capital, then the firm would have a problem to solve, which would be how to minimize the cost of meeting demand. But if you were to do that, you would still ultimately end up with an equation with the same form, because there will be an optimal capital labor ratio that everyone has to satisfy. Now let's impose that supply for the intermediate equals demand. What does that mean? It means that we have to go up here and bring down this equation and use it to substitute for the demand for individual intermediates, like so. We can do some simplification, because clearly if we rearrange this as follows, it becomes clear that this is simply 1 minus epsilon, and this makes the formulation of the firm's problem much easier. Now let's think of the problem of a firm that is choosing P sub T of J, which they might find themselves attached to going forward, as well as being forced to meet demand at that price. They would need to solve the following problem. They're maximizing the choice of that price given the following. They may potentially be stuck with that price forever. So let S be subsequent dates when they might be stuck with that price. Phi times S is the probability that they're still stuck with that price at that date, right? And let D sub T plus S, because T is the current date and S is a future potential date. This is going to be their discount factor, which we'll come back to in a second, times profits at date T plus S. Now, what do we know? First of all, as discussed in a previous video, we know that the stochastic discount factor, D of T plus S, is equal to the expected value given the information set at date T of beta to the S times margin utility of consumption at date S divided by the marginal utility of consumption today. So the firm's problem is the following. And since this is a constant, we can actually take it out. We can rewrite this using this equation where we have to appropriately update all these terms. Notice the one term we do not need to update is the price that they are choosing right now. Then the first order condition is going to be that the derivative of these terms all have to equal 0. So let's take the derivative of these terms. First, it will be easy to distribute the summation term across these two parts. And now, distributing the exponents between top and bottom here, it's clear that this is something that doesn't actually belong in the integral. We can take it out. We can also simplify this as simply p to the epsilon minus 1. And same here. Let's distribute the exponent across top and bottom. And this doesn't have to be here. It doesn't depend on S, so we can bring it out. And we can simplify this also. So deriving this with respect to Pj actually becomes a fairly straightforward task. We multiply by the exponent, subtract 1 from the exponent. Same here, we multiply this by minus epsilon, so we get plus epsilon, and subtract 1 from the exponent, and all this has to equal 0. Now, if we multiply this by minus 1, we get minus epsilon minus 1, and that means that we can move all of this over here. Next, divide both sides by this. We get that. Now let's multiply both sides by Pj. Pj times Pj to the minus 1 is 1. And now let's just divide both sides by this. So finally we have an expression for P of j as a function of a forward-looking series. One last note, notice that every single term on the top is divided by this, every single term on the bottom is divided by this, so we can cancel it and end up with an even simpler expression. Finally, we can rewrite this in the following way. Let x sub 1 of t equals this series, and let x sub 2 of t equals this series. Then two things happen. First, we can write this in the following simpler terms, in terms of x sub 1 and x sub 2. But in addition, notice the following. Let's take x sub 1 and let's separate this between the first term when s equals 0 and the rest. S equals 0, so these terms disappear. So we set all of these terms such that s equals 0. Next, we could set this to s equals 0 as long as we add 1 to everything. But then we could divide everything in here by phi times beta, which would mean that we can lower this accordingly. And then, lo and behold, that means that this whole thing can be replaced by x sub 1 measured at t plus 1. So this has a recursive structure. Also, we can do the same thing with x2. This also equals the first term setting s equals 0, so this disappears. And again, we can set this equal to 0 as long as we add 1 to all the terms here. And then dividing everything by phi beta, and dividing inside, well, what is this? This is just x sub 2 tomorrow. So there you see the convenience of the whole Calvo pricing approach. We are finding that we can reduce tracking the firm's pricing decision to a small number of auxiliary variables.